Hello all, I'm Michael Schertz. I am presenting to you from beautiful Boulder, Colorado, and I'll be talking in this talk about multistate reweighting, a statistical mechanical technique to take information from a number of simulations and use them to predict thermodynamic properties over a range of different conditions. So let me go to the slides and yeah, so this is going to be a guide to multi-state reweighting using mixture distributions, and I'll explain what that is, to better calculate thermodynamic properties from simulation. What are we doing when we perform molecular simulations? Now, let's assume we're particularly using molecular simulations to calculate some sort of thermodynamic averages. And so when we use molecular simulations, we actually are using them to perform Monte Carlo integration of these thermodynamic expectations. So I have some observable radius of gyration, the average value of some dihedral angle. Free energies can also be expressed in these terms as well, as I'll talk about a little later. We're calculating average, and this average is, here's the observable as a function of all the coordinates of the system. We don't want the instantaneous value. We want the average over all the configurations that are sampled in that simulation. So each of those configurations occurs, of all the possible configurations of the system with some probability. And that probability will change, whether it's, as you change the temperature, the probability of each individual conformation will change. A higher temperature, you'll get configurations that have higher energies. If the pressure changes, increased pressure, you'll get higher probabilities of distributions with lower volumes, and so on. Okay, so instead of doing this integral, I mean, it's hard enough to do like three-dimensional integrals. You try to do integrals of all the, you have 10,000 atoms, you've got 30,000 degrees of freedom to integrate over. Instead of doing that, what we do is we replace it with a sum over observations that we get from the simulation. Now, how can we replace this integral times a probability distribution with a sum over observations? Well, if those observations are sampled from the probability distribution of interest. So that's the key. Instead of multiplying by the probability distribution, we collect samples with that probability distribution. And so then we generate samples from our probability distribution using some form of Markov chain Monte Carlo. Well, for example, molecular dynamics uses small collective moves, which with 100% acceptance rate at the cost of usually a negligible error, and that will be generating samples from the desired Boltzmann distribution. When we're doing molecular dynamics, just apply Newton's equations of motion, F equals ma, and we get the positions as we calculate the forces, as we solve this coupled PDE by finite difference. And that's what we're doing. We run a simulation, we gather data according to the Boltzmann distribution, and then we compute our averages just by summing them up, by adding up all the values and dividing by 1 over n. So I'm going to now talk about a statistical technique called importance sampling, which saves us from having to do a lot of conformational sampling in a number of cases. So we've got this integral of interest, which is our expectation value of some observable, with some given probability distribution carried out at a given temperature. Now, we're going to do what mathematicians always do. We're going to multiply by 1, but not just any one. We're going to multiply by pj of x divided by pj of x, where j is some other distribution. Maybe it's some other temperature. Maybe it's a simulation with one of the parameters of the model tweaked a little bit. And so it's a different distribution than pi. You have to be a little careful with this pj. You need to make sure that it's not 0 anywhere, right? Or else that ratio will just blow up. But otherwise, this holds in general. Okay, so we're multiplying by 1, so it's still the same inside the integral. And now we just switch things around. So we put the pi on that fraction, the pj, multiplied by our observable as a function of coordinates, okay? And so when we do this, we can notice, well, now we can do this integral using Monte Carlo integration, but instead of using samples from distribution I, we use samples from distribution j, right? We sample our configurations from distribution j. And so for some reason, it's hard to collect samples from distribution I, or we don't want to, whatever, or we've already got samples from distribution j. We can calculate the observables in distribution I by simply multiplying each observation by the ratio probability of I divided by probability of j. So the sampling is from one distribution, but the observables, all the integrals, are using a different distribution. So if the pix divided by pjx is similar in magnitude as the coordinates varies, then we can avoid generating this entire Markov-Karloff chain. We don't have to run the simulation again. We can just reanalyze with this additional factor. Now, of course, if pi over pj is usually very large, especially if that ratio changes a lot, then this doesn't work so well because you're multiplying your observable by a bunch of random numbers. And one of those ratios is going to be much bigger than the other. It'll dominate the average. So your average, instead of using thousands of samples, will use like one sample. So that won't work. So you really need the pi over pj is relatively similar in magnitude. How similar? That depends on the situation. Okay. So for physical problems, of course, we know these distributions, and it makes it pretty straightforward to apply the ideas of importance sampling. In particular, we know that the probability of observing our confirmation would be proportional to e to the minus beta energy under I. There could be energy due to some difference in the Hamiltonian or whatever. And therefore, the P of I is so that's a constant proportionality. P of I is going to be equal to that factor, e to the minus, the Boltzmann factor, e to the minus beta ui, divided by the partition function, which is just the integral of the Boltzmann factor over all of the configurations. Now that is an exact, that's an equality now instead of just a proportionality. And we could rewrite this. I kind of like this way of rewriting it, that pi of x is equal to e to the beta free energy minus beta times the energy. So that's putting the normalization into the exponential. And it's kind of nice to work with that in a lot of different cases. Okay, so that's our probability in physical cases, assuming we're simulating in the canonical ensemble, the NVT ensemble. We can simulate in a lot of different ensembles as well, of course. But I'm using the canonical ensemble, and this theory's worked for all the other ensembles. It's I'm taking the canonical ensemble specifically here to understand what's going on. We need to calculate this factor, this ratio, pi over pj. So just copying from the previous lines, it's going to be e to the beta ai minus beta ui. So where the free energy will be different as our energy changes, and in the denominator, beta aj minus beta uj, and that'll just be e to the beta change in free energy going from one probability distribution to the next, to minus beta times the change in the energy as a function of configuration. So for each configuration, we evaluate the energy of that in both the current state, we're sampling from uj, and in the state ui. So if we've changed a parameter of the model, we have to just recalculate the energy there. But then we can calculate this factor. So saying that the two probability differences are relatively similar is essentially the same as that the energies can't be too different from configuration to configuration. Okay, so plugging this in, we have our ratio here, we have an observable. So our observables in state I are going to be just 1 over n times the sum of all our observations multiplied by this factor. Now, if we have each individual configuration, we can calculate the change in energy from one configuration to the next. But what about this free energy? How do we calculate the free energy difference between the two states? Well, here's a trick. What if I plug in the value 1 for my observable? Now, clearly, for every different configuration, 1 is 1. And the average of 1 over all configurations is 1 as well. We see that e to the minus beta free energy difference is just equal to the average of e to the minus beta energy difference of each configuration. So all the configurations we sample, we take the energy differences between the two models, multiply by beta, exponentiate, average that, take the minus log, and that is going to give us the free energy difference. So we've got the free energy difference that we can plug into this equation. Now, if you are familiar with this, this is simply the standard Zwanzig method for free energy differences. And then we can plug this all in to our expectations. So what we can do, we can carry simulations at one state. And if we keep track of the energies to go from one state to the next, then we can calculate all of our observables at a new state as well. So we carry out one simulation and then tweak a parameter of the simulation and calculate the properties at a different set of parameters. So that's the idea. One question is, what if you're interested in calculating properties over a large range of parameters, what simulation do you pick in order to reweight? How do you optimally pick your simulations to run so that then you can reweight at a lot of different values? Let's say that I have one particular simulation and I'm interested in properties that are a function of some arbitrary coordinate here along the x-axis. Well, I run this one simulation and that will tell me when the simulation is near this coordinate, but that's it. If I'm interested in what the function, the property is as a function of these coordinates, that doesn't really help. Well, I could carry out another simulation, maybe a few more simulations, and together all of these simulations do visit all the coordinates. But if I'm interested in properties around point 4, which simulation do I use? Do I use this simulation or this simulation for my important sample? And the key trick here is to recognize that you use all of them. You just take all your data and you create a new probability distribution. That is literally just, you throw them all in a pot and all those samples form a new distribution that is just, there's 5 of them and you're equally weighting all of them, 1/5 P1 plus P2 plus P3 plus P4 plus P5. And that is a mixture distribution. And if you have different numbers of samples, say that you've got more samples of this 5th distribution, you just multiply by the number of samples, because when you throw them in a pot, you're going to get more samples from that. So as I was saying, this is called a mixture distribution because it's a mixture of many simulations. So that's sort of the key. If you want to be able to reweight to a large number of different states, rather than coming up with a single distribution that samples all the configurations of interest, you figure out what the configurations of interest are, which can be a little hard sometimes, but sometimes it's straightforward. And you just run separate simulations until you've covered that range. And then you can go back and calculate any properties in that space afterwards. So I've published, with my collaborators a while back, a paper called the multistate Bennett acceptance ratio, which is a paper and a complicated name. And these are the formulas that we came out for calculating energies. If you run simulations at n different states, and you are interested in the properties at those states, then you can run the simulations and plug it in this equation to find the free energy as a function of states, and also calculate the observables of these states. So this is a pretty complicated equation, but if you squint it a little, you can realize that actually this looks like reweighting, right? You've got the free energies and the properties at state I. So what is the distribution that we are reweighting from? Not surprisingly, it is the mixture distribution, right? Where you are taking each of the k distributions you simulated from and just weighting them by the number of samples at each distribution. So that's it. So MBAR is multistate Bennett acceptance ratio. And again, I recognize that a number of other people, some before, some after, have come up with variants of this that are essentially the same formula massaged in different forms. But all of these approaches are really just reweighting from the mixture distribution. Important sampling, the statistical technique, from this mixture distribution for all the samples you've collected. So it reduces to a Bennett acceptance ratio, if you're thinking it from a statistical mechanics point of view, or bridge sampling, if you're thinking about it from the statistics point of view. The same idea was invented there as well for 2 states. A weighted histogram analysis method in the limit of 0 with histogram bins. Histograms are really problematic, and this eliminates some of the issues with histograms. You can also see that in a statistical sense, it's the maximum likelihood estimate of all the data collected. If you want to know the maximum likelihood of the free energy differences between the states, given all the samples that you've collected. And is provably the lowest variance reweighting estimator. Of all the important sampling estimators you can come up with, this is the one that has the lowest uncertainty. So for a little more information about how to interpret MBAR as important sampling for the mixture distribution, you could check out this archive article. What useful distributions can we sample from? Well, if we're interested in various properties, there'll be certain reference distributions we're interested in and target distributions that we're interested in. So for example, if you're doing some temperature scan, then you can run samples at just a few temperatures and then calculate the properties at all of the intermediate temperatures. I didn't make temperature a function of our index I, but it turns out you can do that as well. You can look at distributions corresponding to simulations for different temperatures. Free energies of binding, you run your simulations at several different values of some coupling parameter where you're turning that the drug on or off, and then you're interested in the free energy difference. Specifically, you're interested in the free energy difference between your initial and your final coupling parameters. Potential of mean force, you run a simulation with several different coordinate biasing potentials. So what you're interested in is the unbiased model, what the entire distribution along some collective variable would be if you ran that simulation without biases. And finally, parameter scans. If you're interested in doing some sort of force field optimization, you have some reference model parameters you use, and you figure out what the property behavior would be at with new model parameters. So these are all different ways you can use multi-state reweighting. What physically is MBAR producing? What do you get out of this? So one way that people calculate physical properties a lot is by accumulating a density of states, and you can that's a function, a count of configurations that have a given energy. And if you're interested in properties using the density of states, then you can calculate your averages. You sum over the bins. You have your observable, it's a function of energy multiplied by the density of states, and e to the minus beta e, and you can get properties that way. But a way to think about MBAR is that for each observation in the state of interest, you assign some weight. If it's in one temperature, you assign each sample a given weight. If you're sampling with another temperature, then each sample will get a different weight. If you're simulating a higher temperature, then higher energy observations will get slightly higher weights, and lower energy observations will get lower weights, because at higher temperature, all the distributions are less, the probability of the distributions are flatter as a function of energy. So the probability density that you're getting out here is a weighted sum of delta functions. Each observation will contribute a delta function. The height of that delta function will depend on the weight assigned by MBAR. And so your probability distribution as a function of your configurations, it's a discrete distribution, and it's the sum of the weights times some delta function, where it's data is present where you had an observation. And if you never observed a certain set of coordinates, then it's not, you didn't observe it. We have no information from that. So these are not good at visualizing. A bunch of delta functions are really bad for visualizing, because higher probability density means denser delta functions. That's pretty confusing. But it's very good for computing integrals in high dimensions, right? That's what we're interested in doing. If you take a delta function and integrate it times some arbitrary function, you get out the value of the function where that delta function is centered. And so therefore, that's exactly how we turn our integrals observables into sums over observations. Okay, so that's the basic idea behind MBAR. So it's great, sometimes only marginally more great than other methods. Here's a benchmark test for free energy calculations that we set up. Doing things like the salvation free energy of a Leonard-Jones particle in water. That's about the simplest thing you can do. Switching dipoles, changing it, if you have a positive negative dipole, calculating the free energy to switch that should be 0, but it requires quite a lot of thermodynamic work to do. Or disappearing a large anthracene molecule. So these are rigid molecules, so there's not really much conformational vibration. You're just looking at the efficiency of a method to disappear the whole thing, to make it disappear in water so that water could come in and occupy that space. So this was published a while back in JCTC with one of my graduate students, Himanshu Paliwal. And so what we actually did, we were interested in understanding how good these uncertainty estimates were. So we just repeated the calculations 100 times. We actually calculated a sample uncertainty and compared the analytical uncertainties from different methods with the actual sample variance. So we used about 10 different free energy methods to do this. And so what we get for each of these, we look at the actual uncertainty. So we have 3 different ways of calculating the uncertainty. The analytical uncertainty. So a nice thing about MBAR is that it actually has a formula for the uncertainty. That's true, in the large end limit. So that's great. Are you always in the large end limit? There's some cases when it may fail, but it's nice to have a pretty good analytical uncertainty estimate. The sampled standard deviation, we just take the standard deviation over 100 observations. And a bootstrap uncertainty. This is something that's worth looking up if you haven't seen it before, looking up the bootstrap uncertainty, which is a cool way of calculating uncertainty from just a single sample. And so you can see that MBAR is the lowest uncertainty method, although there's, it's about as good as thermodynamic integration. Some of these other methods are not so good, but it turns out it's about as good as BAR. There's one interesting factoid here. You notice the analytical uncertainty estimate for BAR is an underestimate. Because it assumes that the samples from the two different, it assumes that free energy estimates from state 1 to 2 and state 2 to 3 are independent, which is not actually true because you use the same data to calculate the free energy difference from 1 to 2 and from 2 to 3. Okay. So it's great. If you use other methods and you're careful about it, you'll get answers that are just as good as well. So notice that these actually, this is important, these are all uncertainty estimates. So these are the error bars. So the error bars here are actually the uncertainty in those error bars. Okay. So we can use reweighting to rapidly validate simulation parameters for calculating free energy. So this is, I think, a really cool study. What we were interested in is figuring out exactly how precise you needed to set settings when you're calculating free energies. What did you need to do? The cutoffs, the Ewald parameters, all these complicated parameters. How well do they have to be set in order to get very good free energy estimates that didn't depend on the choices of those parameters? So you can run one simulation and say, how dependent on the cutoff is this result? Now, what you'd think we'd have to do is run their simulations at a bunch of different cutoffs and then compare them and see how different the free energies are. But what we said is, the simulation that's performed at 0.9 nanometers, it will have very similar energies to the simulations performed at 0.95 nanometer cutoff. They'll be different, but they'll be pretty similar. And that's where multi-state reweighting works really well, when the potential energies are actually relatively similar. Okay, so what we're going to do is with these sets of K simulations at M parameter sets, when you're calculating a free energy, you need to run out a series of simulations at different intermediate states. So that's a lot of simulations to do. So we'll just carry out the simulation at 0.9 nanometers, and from the energies of all these states, so we do have, we have a bunch of simulations that we carry out with just one cutoff, and from those set of simulations, we'll evaluate the samples at all the other states as well. So that'll allow us to compute the free energies of all the states considered together. So we just carry out these simulations, and we calculate the energy difference to all of these simulations. So we can use data from one parameter set to predict the change in free energy from fully accurate converged parameters. So for example, this is what it looks like. You're looking at the change in free energy between the very most expensive parameters and all the other parameter sets, right? So we've got, Coulomb distance in nanometers, PWE order, Ewald tolerance. We're considering them all simultaneously. We can do these large multidimensional scans, and we actually only carried out one simulation. The rest of these are looking at the free energy differences just by reevaluating the energies at a few configurations. So, and allows us to identify simulation parameter choices with negligible difference from actually very expensive calculations. So here, delta GB, that's the free energy difference obtained with our initial parameter set. Delta GE is the same simulation done with expensive parameters, and delta GO is with optimized parameters, ones that give the same results as the expensive parameters, but are much cheaper. And so we carry out our initial state sampling. And so this is filled in because we did the simulations with this initial state. And we have an optimized state, which at first we don't actually carry out any simulations for, and an expensive state where we have very long cutoffs, doing very tight spacing in the Ewald summation and the generation of the mesh. And so we estimate the free energy between the initial state and the optimized state, the free energy from this B, our initial simulated benchmark state, to the expensive state. And most importantly, we estimate the free energy difference between the expensive state and the optimized state, though we never actually do that simulation, at least until we do a verification at the end. We just do simulations here, and we calculate this free energy difference using multi-state reweighting. And so this is what we get out for anthracene salvation. This is one of the harder problem there. So we see that our free energy difference between our initial states and our expensive states, it's actually 0.6 kcals per mole, which you'd like to have something a little more accurate than that. Again, these are predictions using only the benchmark states. We said, okay, yeah, this is the free energy difference to expensive parameters. We, with all these evaluations we did, we can identify a set of optimized parameters that differ from the expensive parameters by a very small amount. Instead of 0.6 kcals per mole, 0.03 kcals per mole, within noise. So those are about the same cost as our initial benchmark parameters, but they are much more accurate. So now one thing I said that what you'd like to do is, hey, I'm going to go and just run simulations at a bunch of different, under a bunch of different conditions. But if you did that, what you discover is, if you're looking at the difference between the benchmark state and the expensive state, it would be, you get a lot of noise here, minus 3.36 plus or minus 0.173 kilojoules per mole. Like, is that noise? Is that signal? You don't really know. What MBAR allows us to do is to get rid of that noise between the two different sets of simulations. I'll talk about a little bit about that in a second. And so then we can go back and just run simulations. Now, we run simulations with just the expensive and the benchmark, and we get almost the same results as we did when we just ran the benchmark simulation. Now we're running sets of two. Same here, running sets of two. And here we get when we actually do run both the expensive and the optimized free energy simulations, we get results that are right within 0.03 kilojoules per mole. Yeah, so those are the directly calculated free energy differences, which is exactly the same, to well within statistical noise of what we calculated to begin with. Yeah, so compare those, everything's right on. The ones using both simulations, the one only using one simulation. And a key here that allows us to make comparisons with this little statistical noise is an important thing about MBAR. What we're interested in is the uncertainty between the free energy difference from sets of simulations 1 and the free energy difference from sets of simulations 2. And if you remember correctly, if you have a difference between two things where there's not very much difference between them, you have a really hard time calculating it because the variance of the difference is going to be equal to the sum of the variances if they're assuming they're uncorrelated. But in this case, all the free energies are correlated because we're calculating them from the exact same simulation, or simulations if we were doing some multi-state. And therefore, that's the equation if they're uncorrelated. If they're correlated, you actually have this additional term here, minus 2 the covariance. And what MBAR allows you to do is actually calculate the covariance as well. So you can make even more precise measurements, much more precise than if you had just run two independent simulations, because you can get the correlations between those two simulations as well. So that's a very key part that allowed us to do this study. Okay. It can be used to fill out a multidimensional thermodynamic space, as I mentioned before. And we're not the only ones doing this. This is some great work that was done with some of our Charles Abreu and Ed McGinn, looking at filling out the properties of certain gases and gas mixtures. And the great thing is that they carried out a number of simulations and then used MBAR to fill in all the rest of the thermodynamic space. And I really like this way they phrased it, that it can be seen as a numerical equation of state, which I think is quite cool. That you have lots of numerical equations of state in chemical engineering, and this is really a way of constructing a numerical equation of state given a set of simulations, which I think is quite cool. I really like that they made that observation. So we can use these techniques to scan molecular simulation parameters. This is something that we've done, our own version of this. So we're sort of interested in solvation in water a lot. So here's an example of a Leonard-Jonesium solvated in water. So what I mean, it's a Leonard-Jones particle. And so Leonard-Jones particles have the energy, the pair potential is equal to some energy scale times a sigma over r to the 12th minus sigma over r to the 6th. You have sort of a well depth and then a particle size. So there's two parameters. And so we were interested in how quickly can we calculate the free energy of solvation of a Leonard-Jones particle of essentially all molecular sizes in water. So we started with 10 molecules, linear in volume space. and predicted the free energy of solvation among a 2D grid of states. So we're able to get pretty good results right off. With just 10 simulations, we were able to calculate the free energy of solvation for particles, in a huge range, of size from, point, we went from about 0.6 in size to 1.2 nanometers. So and epsilons ranging from essentially 0 to quite deep potential wells. So one thing you notice here is that the uncertainties were quite bad below 0.4 because we actually didn't really sample that space that well. We did do this simulation, but we really didn't do any in this range at all. So the great thing is, because MBAR gives uncertainties, we were able to detect that and run another simulation right in this space here. And so we're able to fill out this whole space, all the way from united atom methane, neopentane, buckyball sphere represented by Leonard Jones. So, we were able to cover this space of chemically realistic Leonard Jones spheres with just 11 simulations, down to quite high accuracy. So this was what I think pretty cool. This is led by Levi Maiden in my group. So that's just an example of how you can do these molecular scans. To calculate these 28,000 salvation free energies, once we'd done the simulations, only took about an hour on one CPU to go through it and reanalyze everything. So what about free energies of 3 parameters? So if you're interested in ions, a lot of ions are modeled nowadays by Leonard Jones spheres, but with charge added. So you have epsilon, sigma, and Q. So it's a 3 parameter space to search over. And so we're looking at sigmas from 0.3 to 0.9. That's pretty much the range that's used to model ions. Epsilons from 0.1 to 0.8. So I've got here in the upper graph the free energy salvation, and then the uncertainty in that prediction below. And efficiency notes on this, running about 16 CPU hours per simulation to actually do the simulation, and then about 25 CPU seconds to compute potentials. To do all the analysis together takes 5 minutes to 7 hours to compute the free energies, depending on where in the process you're doing. So Levi came up with some very clever adaptive techniques to look over this. And it turns out we only needed about 203 sampled states, so about 3,300 CPU hours, not very much nowadays. And we got this whole grid of salvations from Q equals +2 to -2, this whole range of sigma and this whole range of epsilon with just 200 values. So let me play a movie showing what's going on here. And remember, we've got 3 dimensions. So we've got the free energy of salvation of this ion as a function of epsilon, of theta, and then I'll show over time as a function from Q equals -2 to +2. So you can see, from very large to very small salvation free energy, but the key is the uncertainties are always staying below about 0.56 kcals per mole. Let's look at that again, just to see it again. Yeah, so very large free energies when you have large charges. And so these are the free energies of salvation of the ion. So all of this, with uncertainties over this entire space down to half a kcal per mole, all from just about 200 simulations. So we thought this was pretty cool. Now you might say, well, why should I care that you can do that fancy pants calculation? And I think the key is we can do things like test salvation for energy to analytical theories with unprecedented level of detail. For example, a common approximation that's used is the difference between explicit salvation and Born salvation theory, which you can write, just in terms of the charge and the size of the ion. But of course, there's asymmetry in salvation of charge in water, right? If you look at the charge of -1.2 and 1.2, you can see quite different free energies. These are of the same order of magnitude, but you've got quite different free energies that are being observed here and here. So we're still working on this. We'd love to collaborate with people that are interested in coming up with better salvation theories, given this very precise atomistic data. These are just a few things we've done with multi-state reweighting. There's a selection of a bunch of other papers. They're looking at coupled binding and folding of modeled proteins. We're looking at both temperature and adhesion strength to a wall simultaneously, looking at phase-space mapping between distributions to improve mixture distribution overlap. There's some really cool theory in there. Reweighting cheap trajectories to obtain expensive thermodynamics, doing simulations at going to QMMM simulations and going to polarizable force fields, determining transport properties by reweighting correlation functions. I mostly talked about equilibrium, but in some cases you can look at transport properties as well, calculating phase diagrams by reweighting to different temperatures and pressures, performing Bayesian inference of force field parameters because you can calculate this full surface of force fields, and calculating free energy surfaces, whether in 1D or 2D, calculating potentials of mean force, a fun way to do that using multi-state reweighting. So, and many other people have come up with many other applications for this, but hopefully this talk gave you a little better sense of what the theory is doing and how it could be applied in different situations. So I want to finish with acknowledgments. Thanks a lot for my group for learning new and cool ways to use multi-state reweighting. I especially want to recognize alumni of this project, Himanshu Paliwal, who did the benchmarking, the comparison of error efficiencies, and the looking at different efficacy of different parameter sets for free energies of salvation. And so Himanshu is now an assistant professor at IIT Ropar in India, one of the newer IITs, and Levi Naden, who did the free energies as a function of multiple parameters, and especially the really cool adaptive identification of which states needed to be sampled most. And he's now a software scientist at Mulsi. So thank you so much. In the YouTube video of this that's posted, please put comments for how this could be improved. I'm sure there's ways this could be communicated more clearly, errors that could be avoided. I'll plan on updating this, every 6 months for a year. That's the hope. So put any comments, and I'd love to incorporate those comments in order to make this different versions of this video more useful to you. Thanks so much for listening.